Hello, my name is Christian, and I'll be going over today's tutorial. Now, this is part 2 or phase B out of a 5-part workshop series. Here, we're interested in optimizing a composite material. In this example, what we're going to do is a very simple ply number optimization. Basically, we want to determine how many plies do we need to carry the load given a few load cases. Now, here we're going to be assuming we're dealing with fully continuous plies. We're not going to be using ply drop-offs yet in this composite workshop. When we will consider ply drop-offs is going to be in phase D of this workshop. So again, today you're dealing with phase B, which is using fully continuous plies. But in phase D, that's where you can start introducing ply drop-offs. The reason I want to use fully continuous plies today is it's going to serve as a baseline. Later on, when we start introducing ply drop-offs, we want to make sure that we're actually producing a lightweight composite, and we need a design to make a comparison with. So in this example, we're going to be creating that composite in which to perform comparisons with. Here, just to give you an example, we're going to start off with this composite configuration. You'll see that we've defined a few plies here at the top. These layers that you see here, these layers are going to be allowed to change in thickness, whereas the top plies are going to remain fixed in terms of thickness. So here, if you look at the before and after, you'll see that the top plies remain fixed in terms of thickness. They will continue to be 0.125 millimeters in thickness, but it's only these internal layers that are allowed to vary in thickness, and this is how we're going to perform the ply thickness in this example. And you'll notice that the weight is going to be reduced from about 5 to about 2 or 3. And at the same time, we're going to be satisfying our max failure index of 1.0. So before we had a max failure index of 0.235, but at the end, we'll still be under and have a new value of 0.934. Now, those who have followed the previous exercise may recognize that the load for this model is going to be the same. We still have a fixed edge, and we're going to apply 2 load cases or 2 loads at the free edge here on the right. Now, it's worth briefly mentioning the configuration of the P-comp entry. Here, I purposely defined 4 layers at the very top. So these are going to be these 4 top layers. These 4 top layers are going to remain fixed during the optimization. So these are going to have a thickness of a ply, so 0.125 millimeters. I recommend always using if you want to track responses like ply stress, ply strain, a failure index, or strength ratio, I always recommend fixing a few plies at the outer fibers for a composite. This is so you can accurately track these ply stresses, these ply strains, and so on and so on. I talk more about this in the appendix. So if you want to learn more about why I'm using this particular configuration for the P-comp entry, I suggest you go to the appendix and read up a little bit more on why that is. So again, just to reiterate, I'm using fixed plies here in the middle, or at the outer fibers, and only the interior layers are allowed to vary during the optimization. And since we're using the symmetry option for the P-comp, we only need to define only the first half layers of the composite, and then Nastran internally will create the mirror layers, if you will, across the line of symmetry. So if you look at the P-comp, we've only defined the first half of the layers, and then again, Nastran will know to create the other half internally. Here's just a repetition of what I mentioned a moment ago. We're going to leave the outer plies fixed. The thickness will remain fixed. For these fixed plies, we will track the failure indices, or you can track the ply stresses and ply strains. What we're going to vary in this exercise are the thicknesses of the interior layers. That's the only thing that's going to change during this optimization. These layers that you see here marked are going to be changing in terms of thickness. And let's suppose you're not dealing with angles such as 45, negative 45, 90, and 0. The same applies whether you're using other angles. Here I'm using angles such as 80, negative 80, 65, and negative 65, and 0, or the 0 is the core. Here, what I do for this configuration, again, I fix plies at the outer fibers. So here, the first few layers are going to be fixed. You notice that the ply thickness, or the layer thickness, is 0.125, which is the ply thickness. So those layers are going to be fixed during this optimization. It is the other layers 5 through 8, that I'm actually going to be varying during the optimization. So even though here I'm only using angles positive, negative 45, 90, and 0, and I'm using this configuration for the P comp, you should follow the same format for other angles. So that's what I'm just saying here in this P comp entry. Again, you can go to the appendix and read up a little bit more on why I'm using this particular format. Here on this slide is the problem statement. As always, I recommend everyone taking a few minutes, sit down, get a piece of paper, draft out what your variables are, what your objective is, and what your constraints are. Since we're dealing with the gradient-based optimizer, your objective function must follow the rules that you learned in calculus. The objective function must be differentiable everywhere in your domain or your design space, so you can calculate the gradients, if you will, of your function. Sometimes, personally, I don't select a correct objective, and then I run into problems later on during the optimization. But if I draft out the problem statement, I can make sure that my variables, my objective, and my constraints are going to be okay when it comes to optimization. So that's why I always recommend drafting out your problem statement. So here we're dealing with a few design variables. When you're programming all of this into Nastran, you can select variables in terms of thickness, and that's what we're going to do. We're going to set the thickness of these interior layers as design variables. So if we go back a few slides, this red layer, we're going to set the thickness of this layer as a variable. We're going to set the thickness of this layer as a variable, and we're going to repeat the process for the 90, positive 45, negative 45, and 0 degree layers. Again, this is only happening for layers 5, 6, 7, and 8. Layers 1, 2, and 3, and 4, they will be left untouched during the optimization. We are only going to vary the thickness of layers 5, 6, 7, and 8. Since this composite is symmetric, this will also modify layers, layers 11, 12, 13, and 14. So that would be these layers also. So these are the only thicknesses we're going to allow to change during this optimization. Now, we don't want to work in terms of thickness. We want to work in terms of number of plies. So we're going to define the single variable number of plies. Here, what we're going to do is say that whatever the thickness is of these plies, we're going to have one independent variable number of plies that's going to control all the thicknesses of these other layers. So here we're going to say that, okay, let's suppose that y1 is the number of plies. We're going to multiply it by the ply thickness, 0.125. And then all of these thickness variables, 1, 2, 3, and 4, are going to equal this product of y1 and 0.125. So again, we're going to create these thickness variables, but then we're going to create this other variable, y1, that's going to be the number of plies variable. And then we're going to relate the thickness with this number of plies variable. Here, we want to minimize the weight of this composite while making sure that the failure index of these outer plies, which again are the outer 1, 2, 3, and 4, 15, 16, 17, and 18 layers, we're going to make sure that the failure index is less than 1. Now, here I'm using an upper bound of 0.95, not 1. The reason I'm using 0.95 is the following. Sometimes when you're done with the optimization, you'll get a slight violation of your upper bound. So here, let's suppose I use an upper bound of 1.0. The optimizer might produce a design that has a new failure index of 1.01. For the optimizer, it's difficult to arrive at an exact solution. So we have this small, allotment. We have a cushion. We allow some degree of violation of the constraints. But here we don't want to have anything more than 1.0. So here what I'm going to do is I'm going to say my upper bound is going to be 0.95. So at the end, we might get a value of 0.95, or here, maybe we'll get a value of 0.961. Maybe we'll get a value of 0.962. So here, again, we still allow some violation of the constraint, but we are nowhere near a 1.0, which is what we want to avoid in this exercise. So that's why I'm using 0.95. Alternatively, if you really wanted to, you could use 0.98 or 0.99. But again, you risk getting really close to maybe 1.01, maybe 1.02. But if you use 0.95, you'll definitely stay away from the upper bound of 1.0. Okay, now before I go ahead and move on to the tutorial, let me just go ahead and mention that if at any time you have questions, if you want training, not necessarily with the optimizer today, maybe you want training with machine learning, you can contact me at the email address here. If you want access to today's software, you can also contact me here at this email address. Now, let me jump out of here and let me go ahead and start this exercise. Let me go ahead and delete everything from the downloads directory. Personally, I always like to work with the clean directory. Otherwise, if you have a lot of files in that directory, you're going to start to get confused about what file is what. For this exercise, we're going to look at phase B in the tutorial section. So if I open the composites link and I go to phase B, I'll go ahead and click download here. And then I'll extract this bulk data file. And if I look inside of this bulk data file, I'll notice that this is going to be defining the composite coupon that I showed on the screen a few moments ago. If we look at the pcomp entry, you'll notice that we have those first 4 layers that define the plies. And then you'll notice that the next 4 layers are defining the layers that we're going to modify in this optimization. You'll notice that the thicknesses are not ply thicknesses. They're actually 0.625, which is about 3 plies thick, I believe, or 4. I have to do the math again, but just know that these layers, if you will, are going to be aggregate layers, if you will. They're going to be used to define multiple plies, if you will. So now let's go back to the web app and open up the optimization web app. I'm going to go ahead and upload that bulk data file. And we'll click upload. Now, the first step is defining those thickness variables. And here, if I look at the diagram, I want to define thickness variables for layers 5, which is this red layer, layers 6, 7, and 8. Today, we are not dealing with the core, so don't worry about layer 9. And remember, we are going to leave the top 4 layers alone. The top 4 layers are going to be the plies, and here we don't want to modify these top 4 layers or plies. So if we look here at the table, let's go ahead and type in thickness. And now I get a list of all the thicknesses I can optimize. Remember, layers 1, 2, 3, and 4 are left untouched. I only want to set the thickness of layers 5, 6, 7, and 8 as thickness variables. If you look here on the next table, I have my thickness variables. You don't have to modify these, so just continue on. We're going to create one variable called y1. This is going to be our ply number variable. So if I click on options and label comments, and I click on options again to close that, here I'm going to say that this variable is number of plies for layers 5, 6, 7, and 8. So that's a description of this variable. Here I'm going to say that I'll start off with one ply, and I'm going to let the number of plies range between 1 and 200. I don't want to end with fractional values for the ply number variable. I want specific integers for the number of variables. So here I'll say that I want the values to take on integers with this expression. So use values of 1, 2, 3, all the way to 200 in the increments of 1.0. So now the last thing we have to do is link this variable, the number of plies, back to the thickness variables. So how do we do that? We'll go ahead and create 4 d-links, and I'll say here that x1 is going to equal to y1 times 0.125 millimeters. And I'll just repeat the process here. x2, x3, and x4. So all of these thicknesses for these layers are going to be associated with this single ply number variable. Alternatively, if you wanted to just combine all of this, x1, x2, x3, x4 is equal to y1 times 1.25. You can also do this, but here I'm going to separate them out as you see here on the screen. Now let's move on to the objective. This is fairly straightforward. Just find the response, click on the plus icon, and you've defined your objective. Here we're minimizing the objective, and that's it. Let's move on to the constraints. Here, let's find the failure index constraint, and we'll go ahead and repeat this, or we'll click 8 responses. So click on the icon 8 times, 1, 2, 3, 4, 5, 6, 7, and 8. And let's go ahead and start working on this. Here, we want to call out, we want to constrain the failure indices for pcomp1. So that's what I'm doing now. I'm specifying pcomp1 using these input boxes. And then for the upper bound, remember that I'm using an upper bound of 0.95. You can use 1.0 for the upper bound, but just know that you'll slightly violate the 1.0 bound just a little. Here we'll say that we want to consider only the failure index for the ply and not the interlaminar failure index. And then for the layers, we're only considering layers 1, 2, 3, and 4. So now we're considering the outer plies 1, 2, 3, and 4, and the bottom plies 18, 17, 16, and 15. Now remember, here we're using the symmetry option. So even though you define 9 layers in your pcomp entry, internally Nastran is going to consider these additional mirror layers. So layers 10, 11, 12, 13, and so on and so on through 18. Here, we want to constrain the first 4 plies or 4 layers, and we also want to constrain the last 4 layers or 4 plies. So we need to constrain these layers, 15, 16, 17, and 18. So let's jump out of here and let's go ahead and configure this in a moment. So layers 1, 2, 3, and 4, and then 15, 16, 17, and 18. So there we go. We've defined our constraints for the failure indices. Let me quickly double check this and make sure everything looks good. Okay, 1, 2, 3, 4, 15, 16, 17, 18, pcomp1, and the upper bound is 0.95. Okay, things look good here. Let's move on to the subcases. Now, here you have a few options to assign these constraints to multiple subcases. Number one, be sure to select what subcases you want to work with here. Here I'm only selecting subcases 1 and 2. You can either go checkbox by checkbox and deselect and select the checkboxes. This is going to assign your constraints to these different subcases. Alternatively, you can either uncheck all the checkboxes or mark all the checkboxes. It's very flexible here when you're working with dozens or hundreds of subcases. Once we're done here, let me see in my notes if there's anything else to do. Nope, that's pretty much it. Let's go to the exporter and download my newest set of bulk data files. And we'll go ahead and extract the contents of these files. And then we'll click on Start MSC Nastran to begin this apply number optimization. Now, one comment about the apply number variables. My recommendation in most optimizations is that you start with a feasible design. And then this will ensure, or in most cases, this will help ensure that you get a feasible design at the very end. Feasible means that you're satisfying all of your design constraints. Sometimes the optimizer will wander into the infeasible design space. And other times you'll see it go back to the feasible design space. When you start feasible in the feasible part of the design space, it helps the optimizer stay in the feasible design space. One thing I've noticed when it comes to composite optimization, there are many solutions to apply number optimization. So sometimes what you might end up with is a feasible design that is suboptimal. So let me type this out. So again, let me repeat this. Sometimes when you start with a feasible design for apply number optimization, you'll get a feasible design that is suboptimal. What I found in apply number optimization, if you start with an infeasible design, you will get a feasible design that is more optimal in many cases. So if you notice back at the optimization results, you'll notice that my max normalized constraint starts off with a value of 1.2. If we look at the F06 file, and if I look through the responses at the very beginning, if we navigate to the Lamina failure index section and we look at the responses for failure index, you notice that my initial failure indices are greater than the upper bound of 0.95. And then if we look at the far right hand corner, I get the marker that says, hey, you are violating your failure index constraints. And this is done on purpose. Here, since we have a violation of the design constraint, we're actually getting a positive value of our max normalized constraint of 1.19. Positive means you're violating your constraints. Here, we see the objective having to increase the thickness or the weight to reduce the violation of the constraints. Eventually, we get a constraint value that's close to 0. Here, what we want is a constraint value that is close to 0, and in most cases, we want it to be negative when possible. Here, we have a negative max normalized constraint. If we look back here at the very end of the optimization, if we go up a little, and if we look at the failure indices now, you'll see that the new values are less than the upper bound of 0.95 for both load case 1 and load case 2. You'll see that all of these values are less than 0.95. If you want to explore these responses in more detail, if you go to the results section and you click on responses F06, you can upload this F06 file and you can actually debug the responses. So here we get a look at all the failure index responses. What are their values for the initial design cycle 1, 2, 3, 4, and the very end? What's the final design cycle like? So that's available here in this tool. You can look at the maximum normalized constraint values. So here, if we click on maximum constraint for each design cycle, you'll see that the maximum normalized constraint value is 1.19, which is what we get here in this plot. It's 1.19. And here for the next design cycle, we get a value of 0.412. And if we look back here, for design cycle 1, we now have 0.412, and then we get negative, negative, and negative, which lines up with what we have here in the next few sections, negative, negative, and negative. Again, remember, if it's a positive normalized constraint value, you're actually violating your bounds. If it's negative, you're actually satisfying your constraints. So again, this is the responses web app. You can use this to debug and see what's happening with the responses during the optimization. So here we successfully done the following. We found a feasible design. And now let's look at the apply number variables. So here, if we look at the variable section, let's go ahead and hide all the plots. And we're only going to mark or display the y1 variable, which is your apply number variable. Here at the very beginning, we started with only one ply. Then at the very end, we ended off with this new section that is 2 plies. So now, let me look here on my notes and see if there's anything else to discuss here. Right, okay, so I guess we'll be taking a look at the ply thicknesses. So here, let's go ahead and open up the viewer web app. We're going to open 2 windows. In this first window, we're going to import the original coupon and we're going to upload it. And then if we look here in the directory where we perform the optimization, if you look in workspace B, you'll get an updated bulk data file where the pcomp entries have been automatically updated for me. So here, let me just modify this entry a little. Let me move it to the side. And here on the left is the original bulk data file before the optimization. So remember, we only modify the interior layers. We only optimize the thicknesses of these interior layers. If we look here on the right, you'll notice that the thicknesses have been updated. These are the optimal thicknesses that have been determined during this optimization. Here we just see that the thicknesses are now 0.125. So if you recall here, the optimal number of plies was 2. And if we look here at the bulk data file, you'll notice that the ply thickness for 1 ply is 0.125. When we use 2 plies, it now becomes 0.25. And since all of these layers were linked to that 1 ply number variable, all of these are now using a thickness of 2 plies or 0.25. So if we look back here in the viewer, let's go ahead and turn on all the plies. And let's click this icon to color coordinate the plies. And maybe it helps to look at the background at a different color, and we'll look at the top and let's zoom in. So if we zoom in, this is what the thicknesses of these layers look like before. And let me zoom out a little bit more. So this is what the composite looked like before the optimization. Let's go ahead and upload that new file that's in workspace B. So this is now using 2 plies for each of those 90, 45, and 0 degree layers. And like before, we'll go ahead and look at this with the white background. We'll look at this from the top, and we'll zoom in a little, and then we'll display all of the layers. And maybe we'll zoom in a little bit more. Maybe I zoomed in a little much, so let me zoom out a little bit more. And then here, let me try and adjust this so it's the scales are about the same. So here I'm just adjusting this. And again, I'm trying to translate and zoom in this so the scales in both models are about the same. So just bear with me while I do this. And let me zoom out a little bit more. So before, the thickness of each of these layers was 0.625 millimeters. So that would be these layers. And let me color coordinate these plies. So one comment about these colors, you'll see that the 90-degree pliers are colored red. The positive 45-degree pliers are colored blue. Negative 45 is green. 0 is yellow or gold for the golden plies. And then this beige color is for the core. So now if you'll notice that if we go between left and right, so before and after, you'll notice a few things. Number one, the thickness of this composite is thinner. And the next thing you'll notice, the thickness of these layers, what were they? Layers 5, 6, 7, and 8. And I forget what these other layers are. I believe there are layers 11, 12, 13, and 14. You'll notice that these layers have actually been reduced. So there you have it. We've been able to perform this thickness optimization, which was a ply number optimization. And the reason we did this was to establish a baseline. If we use fully continuous plies, how many plies would we need to satisfy the max failure index of 1.0? We went through the optimization. We found that we need about two plies for each of these 90, 45, and negative 45 and 0-degree plies. And like I said, this is our starting design with fully continuous plies. In one of the upcoming tutorials, we're going to perform, or rather, we're going to introduce ply drop-offs. We're actually going to custom tailor each ply to target these failure indices while minimizing the weight of this composite coupon. So in this tutorial, we targeted fully continuous plies. In an upcoming tutorial, we're going to introduce ply drop-offs. We're going to create these really exotic looking ply shapes. So I already covered this. We already went over all of this. I think we pretty much went over everything so far. So with that, I think we're pretty much done with this tutorial. Again, if you have any questions or comments, as always, you're more than welcome to contact me at this email address. Thank you for watching.